Start with the few questions. The first question is that the gravitational force acting on a particle of 1 gram is due to a similar particle is this. So we have two particles each of 1 gram. So the gravitational force between them is this much, 6.67 into 10 to the power minus 17 Newton. So we have to find the distance between the particles. So the formula for gravitational force, F is equal to G m1 m2 upon the distance square. So the force is given 6.67 into 10 to the power minus 17. The value of G is 6.67 into 10 to the minus 11, and again the mass is 1 gram. So for 1 gram we will have to use in kg as a unit, so 1 by 1000 kg, and we have two masses of same 1 gram, so 1 by 1000 kg upon distance we have to find. R square is to be found out. So R square is equal to 6.67 into 10 to the power minus 11. This will come downstairs, 6.67 into 10 to the minus 17, and this 10 to the power 3 here and 10 to the power 3 here, so 10 to the power 6 will come downstairs. So once you solve this you will get 10 to the power minus 17 upon 10 to the power minus 17. So this will give you 1. So R will come out to be, R square is 1, so R will come out to be 1 plus minus 1, but the distance is not negative, so because of that we will say R is 1 meter. So the particles are separated by 1 meter. Okay. Now in the second question we have to calculate the force with which you attract the earth. So the force of gravity between you and the earth. So question number 2. So what is the force between the man and the earth? So the basic formula is this. So where capital M is the mass of earth, R is the distance between earth and the object. So this force can also be written like this, mg, where g is the acceleration due to gravity, which is equal to gm upon r square. So this is the formula for weight, if you know. So weight is just the opposition to the force of gravity. So weight equal to mg equal to let's say the person is of 50 kg, let's say. So 50 into acceleration due to gravity is approximately 9.8, so let's take it 10, so approximately 500 Newton. So this is the force that is acting on you, this is your weight. So you are also attracting the earth with the same force. Okay, the earth attracts you with 500 Newton, so you are also attracting the earth by the same force, that is 500 Newton. Now in the third question, at what distance should two charges each equal to 1 coulomb be placed so that the force between them equal your weight? So you have to find the distance between the charges. So question number 3. So the force in between two charges is given by the Coulomb's law, 1 upon 4 pi epsilon naught q1 q2 upon the distance square, quite similar to that of the formula for gravity. Okay, so now what we have this thing, this is equal to 9 into 10 to the power 9. We have these two things, both are given to be 1 coulombs. Okay, both are 1 coulomb. We have to find this, and the force. So what is the force acting on you? So let's say again that the force that is acting is gravitational force, so mg, weight. Okay, your weight. So mg equal to 9 into 10 to the power 9 into 1 upon r square. So r square will be equal to 9 into 10 to the power 9 upon mg, g, let's take g to be 10. So 9 into 10 to the power 8 upon m. Now you can take any mass because they are asking you to take your mass, okay, your own mass. So let's say you are approximately, let's say 64 kg. Okay, so what you will get, R equal to root 9 into 10 to the power 8 upon 64. So 3 into 10 to the power 4 upon 8. Okay, so this will give you approximately 3750 meters. So if the force between two charges has to be equal to a weight, then the 1 coulomb charges are to be placed this much apart. It is approximately 3.75 kilometers apart. Okay. Now in question 4 we have two spherical bodies and the masses of both the bodies is 50 kg and the separation is 20 centimeter. Then we are placing equal charges on the bodies, so they will obviously repel because same charges repel each other. So they will try to go away. So there are two forces. Gravity is trying to move them close together, and the repulsion force is trying repulsion due to Coulomb's electric force is trying to move them apart. So we have to find the magnitude of the charge placed on the either body if the force of repulsion and force of attraction due to Coulomb's force and the gravitational force is equal. So fourth one, so let's say the mass is 50 kg, distance is 20 centimeter, that is 0.2 meter. So gravitational force will be equal to g m1 m2 upon the distance squared, which will be 6.67 into 10 to the power minus 11 into 2500, because both the objects are of 50 kg. So 50 into 50 is 2500 upon distance square. 0.2 square means 0.04. Now the Coulomb's force will be equal to 6.7 into, sorry, it will be 9 into 10 to the power 9 into q square, because both the charges will be same, q square upon the distance is 0.04. The distance is obviously same in both the cases because the distance is 0.2. okay, so now this force, Coulomb's force, is equal to gravitational force, so we can equate the two equations, first and second. So what we will have 6.67 into 10 to the power minus 11 into 2500 upon 0.04 equal to 9 into 10 to the power 9 into q square upon 0.04. So this will get cancelled out. So ultimately q square will be equal to, once you solve this, 18.07 into 10 to the power minus 18. So we have to take the square root. So after taking the square root, you will find that the value is approximately 4.3 into 10 to the power minus 9 coulomb. This will be the value of the charges. Each individual charge must be this much coulomb in order to have the force equal to that of gravity. So let's proceed to the next question. So here we have a monkey who's sitting on a tree limb, and the limb exerts a normal force, upward force of 48 Newton, and the frictional force is 20 Newton. So I have to find the magnitude of the total force exerted by the limb on the monkey. So let's first try to understand what the situation is. So the situation is something like this. It is difficult to draw the monkey, but let's say the monkey is sitting like this. So the normal force is 48 Newton and there is it is slipping like this, so the friction will be opposite to it. So friction will be here, which will be 20 Newton. So these two forces are like this. So you can find the resultant using simple vector formula of resultant, 48 square plus 20 whole square. Because the angle is 90 degree, because of that cos 90 will be 0. So 2 f1 f2 cos theta will be 0. So root 2304 plus 400, 2704. So this will be approx 52 Newton. So this will be the resultant force on the monkey. Now in the next question, there is a bodybuilder who is exerting a force of 150 Newton against a bull worker, and it compresses it by 20 centimeters. So there is this compression. So I have to find the spring constant, okay, of the spring. So let's say the spring is like this. So there is a force which is trying to compress the spring, so there will be a restoring force, okay. So we know that the compression is 20 centimeter, that is 0.2 meters, and we know that the force of restoration is minus kx, or you can only use kx right now. So the force is 150, k is unknown, we have to find this, and the displacement is 0.2 meters. So k will be equal to 150 upon 0.2. So it will give us 1500 upon 2, that is 750 Newton per meter. So this will be the spring constant. Now in question number 7, we have a satellite which is projected vertically up. Now at what height above the earth's surface will the force of satellite due to earth be reduced to half of its value at the earth station? So that is the how much the what height will be the force of gravity will be half that is on the surface. So let's say this is our earth, so there is some force of gravity here, so we are launching it at some height h. So we have to find that height. So let's say the force of gravity is f here, so we have to find the height h where the force of gravity will become half of the force at the surface. Earth station is the surface, okay. So force will be gm upon small m r plus h whole square, and this is at height h, and at the surface formula will be gmm upon r square. This is r and this is height. So now we have been given that the force must become half at the height. So fh will be half of the value at the surface. So gmm upon r plus h whole square equal to gmm upon r square and half, so therefore 2 is also there. So this will get cancelled out. So we will have 1 upon r plus h whole square equal to 1 by 2r square. 2r square equal to r plus h whole square. This will give you r square plus 2rh plus h square. 2r square minus r square minus 2rh minus h square equal to 0. So we get r square minus 2rh minus h square equal to 0. So let's try to solve this. So let's try to solve the let's try to find the value of r or whatever height, okay. So using this formula, minus b plus minus root b square minus 4ac upon 2a. So this is minus 2r plus minus root 4r square plus 4r square upon 2a. A is 1. So minus 2r plus minus 2 root 2r upon 2. So this 2 will become common. So minus r plus minus root 2r. This is that we have now. Let's take r common, so we will have root 2 minus 1 plus root 2, or you can write r root 2 minus 1. So r into 1.414 minus 1, so r into 0.414. So radius of earth is 6400 meters, sorry 6400 kilometers, so into 0.414, so it will give us 2649.6, approximately 2650 kilometers. So height should be approximately this much. I must tell you one more thing. We are solving it for the height, okay? So this equation is like this, and for this we are solving this because we have to find the height. Question 8. So now we have two charged particles and they are separated by 20 centimeters. So the distance between them is 20 centimeter and the force is 20 Newton between them. So now what will happen if the separation is increased to 25 centimeter? So the 8th question. So the first situation is force is 20 Newton and the distance is 20 centimeter. And in the second situation the force is unknown but the distance is increased to 25 centimeter. So we know that F1 will be, or rather F is 1 upon 4 pi epsilon naught Q1 Q2 upon r square. So F is proportional to 1 by r square because this is constant, this is constant in this question, okay? We are not changing charge in this question. So ultimately F1 upon F2 will be equal to R2 square upon R1 square. So we have to find F2. So F2 will be equal to F1 into R1 square on R2 square. So 20 to 20 by 25 square. So this will give us 20 into 16 by 25. So which is equal to 64 by 5, which will give us 12.8 Newton. So approximately F2 will be 13 Newton approximately. So by the ratio, this relation, force is proportional to 1 by r square, by this we have found this value of F2. Now in the 9th question we have a force with which the earth attracts an object. So obviously we know that that force is called the weight of the object. So you have to calculate the weight of the object on the moon using the following data. So obviously the weight will change, weight will be different on earth and weight will be different on the moon, okay? So what we have been given is that this is the 9th question. So first of all we know that the force of gravity is equal to G into mass, celestial body, okay? It can be earth, it can be moon. So let's say for moon m and the mass of the body, so 6.67 into 10 to the power minus 11. Mass of moon is 7.36 into 10 to the power 22 kg into 6 into 10 to the power 24. This is the mass of earth. Then 3.8 into 10 to the power 8 whole square. Distance between earth and moon, so earth and moon. So now the force between earth and moon can be found out by, after simplification you will get 6.67 into 10 to 7.36 into 10 to the power 35 upon 3.8 squared into 10 to the power 16. So the force will be 20.3 into 10 to the power 19 or 2.03 into 10 to the power 20. So the force between earth and moon is approximately 2 into 10 to the power 20 Newton approx. So this is the force between earth and moon. Now question 10, we have to find the ratio of magnitude of electric force to gravitational force between two protons. So for two protons we have to find gravity and electric. So this is 10th question. So the charge on proton is 1.6 into 10 to the power minus 19 coulomb. This is positive value, okay, remember. Now so the electric force will be 1 upon 4 pi epsilon naught q1 q2 upon r square. Both the charges are protons, so 1 upon 4 pi epsilon naught is 9 into 10 to the power 9. q1 q2 are same, so 1.6 into 10 to the power minus 19 whole square upon the distance squared, r squared. Now the mass of proton is equal to 1.732 into 10 to the power minus 27 kg. Gravitational force will be G m1 m2 upon r square, so it will be 6.67 into 10 to the power minus 11 into 1.732 square into 10 to the power minus 54. Square is there, so r square. So let's take the ratio. R square will get cancelled out, so I am directly writing this thing. (6.67 into 10 to the minus 11) 1.732 into 1.732 into 10 to the power minus 54. So once you solve this, Fe by Fg, it will be approximately 1.24 into 10 to the power 36. So this will be the approximate ratio between electrostatic and gravitational force. So you can see that the gravitational force is weaker than the electrostatic force. Question 11. So in this question we have proton and electron. So again we have to find the Coulomb force between them, and let's say if the atom goes into its first excited state, so the distance between electron and proton will increase. That is, electron is jumping into higher orbit, so the distance between nucleus and the electron's orbit is increased. Proton and electron's distance is increased by 4 times. So now again we have to find the Coulomb's force. So we have two situations in which we have to find the Coulomb's force. So this is 11th. So first of all, in the first situation, Coulomb's force will be 9 into 10 to the power 9. 1.6 into 10 to the power minus 19 square, because both are proton and electron have both same charge. Only minus sign is there, but we are only concerned with the magnitude, that's why we are not taking the minus sign. And this is the approximate distance between them. So it will give us 8.2 into 10 to the power minus 8 newtons. So when the electron is in the first orbit or the ground state. Now second situation, this is the first situation. Now the second situation, again 9 into 10 to the power 9, this charge will be same. Now what will change is the distance. So the distance will become 4 times, okay, distance will become 4 times of the original. 4 into 5.3 into 10 to the power minus 11 whole square. So once you solve this, you will obtain 5.1 into 10 to the power minus 9 Newton. So the force, when the distance increased, the force has decreased. In the 12th question, we have a geostationary satellite or geostationary orbit. So what is a geostationary orbit? It is the orbit in which the time period of the satellite is same as that of the time period of the rotation of Earth. That is, the satellite rotates around the Earth in 24 hours, just like Earth rotates on its axis in 24 hours. So the satellite remains fixed in the sky at a location because it is moving with the Earth. So the distance of the geostationary orbit is 36,000 kilometers. Now the weight of the equipment is 120 kg there. So now we have to find we have been given the radius also. So we have to find the weight. Okay, the weight on earth is 120 kg on the surface, but what about the weight on the geostationary orbit, that is 36,000 kilometers above. So 12th one, so here G normally is this. In geostationary orbit it will be like approximately like this. So G dash upon G r square upon r plus h whole square, it will give you 6400 into 6400 upon around 46400 into 42400 into 42400, because 36 plus 6400. So this will approximately will be equal to 0.0227. So G dash will be 0.227, sorry 0.0227 into G, 0.0227 into 9.8. So G dash will be approximately 0.223 meter per second square. So on the at this height, at the height of geostationary satellite, the acceleration due to gravity reduces quite a lot. So what will be the weight? So weight is mg dash. So mass is 120 kg, 0.223. So it will give us around 27 newtons. So the weight will be 27 newton in the geostationary orbit.